to talk about a project that I have been working on actually while being on parental leave. So it's been hacked on in small 1 hour slots for a number of months. It's called Parallel Programming in Haskell almost for free. And it's an embedding of those array building blocks into the Haskell language. So this is something I've been working on together with Larry Sheeran, my supervisor. We wrote the article together, the one that's in the proceedings. So what I would like to do with this presentation is just go over what's in the paper, but at a kind of high level. Not that many details, but I hope to have spark some interest for you to go and look at it yourself in the actual paper. And one thing I would like and welcome is if someone thinks it's interesting and wants to try out this language or want to help with getting somewhere.
Tell us what you've done. I've seen the whole talk with no slides at all.
Okay.
It's cool.
Yeah, but here they come. Yeah. Thank you. Okay, so we covered this. I'm Joel. And the reality today is that we have heterogeneous multi-manicore systems to program, like the sandwich, the Ivy Bridge, and the AMD APUs. They are multi-core processors with integrated GPUs. They have SIMD units, very wide as such in the Ivy Bridge case. So there's lots of parallel resources to program. And usually I think you use all these kinds of libraries like pthreads, OpenMP, SIMD, Intrinsics, and to get the maximum performance out of these. Then we also have discrete graphics, NVIDIA AMD, really powerful things now. And all of these could be, in one machine, or if you have a cluster of them, and then you have lots of stuff to program. So how should we do that? We could use those very specific targeted things for one of the units, or we could try to make some kind of higher level programming language that can be targeted towards either of these hardware platforms in the end. And Intel's array building blocks is one approach to getting some sense of some kind of platform independence by providing a high level programming model that abstracts from the number of cores or SIMD bits or existence of. So they do that by just-in-time compilation towards the architecture they are currently on. EmbArBB, Intel's array building blocks, is composed of a number of things. There's a virtual machine at the bottom that I don't really know how that's implemented, but that takes care of the compilation towards the specific target architecture in the end. But this is how I know it. The C API, that's the collection of functions that let you create programs for the virtual machine. So that one is specified and documented very well. So and also I think the cool feature about the EmbArBB is that they create the C API and open up for other uses of it. With the EmbArBB as you get it when you download it from Intel's website, you get a language embedded in C++ that sits on top of the C API. And this is the part that I've sort of just switched out in my work. Yeah, I was going to say this, the C API. really cool part of the ARBB. It's a platform for implementing other embeddings on top of ARBB, and those embeddings will get the vectorization and threading for free. You create functions in ARBB by calls to this C API, like begin function and function. And then for every operation that ARBB can perform, there is an opcode that you create by using ARBB op, followed by opcode and operands. ARBB ops work on scalars and 1, 2, and 3 dimensional vectors, and also irregular vectors called nested vectors in ARBB in their way of speaking. This is an example of what a small code listing could look like in the C++ embedding. It's a matrix vector multiplication. It uses a number of built-in ARBB functions, the add, reduction, and the repeat row. They are offered to you by ARBB, and they are threaded and vectorized. So you see here that this uses some C++ features like templates and overloading of operators. So this would look very much nicer to work with than the C API directly. But this is from Haskell embedded DSL users' point of view, nothing new, like the overloaded multiplication there, but it's element-wise and things like that we've been doing for a long time. Here is also in C++. So, yeah, there are direct bindings to the VM API. There's just a very direct mapping of the C API into the Haskell library. So for every C function, there's also a Haskell function in these bindings. And I started working with them on them when I was at an internship at Intel with Ryan Newton. And we also started working on an implementation of using ARBB as a backend to data array accelerate, this other embedded language for array computations that right now targets GPUs. We got as far as running some small, very specific programs on ARBB using the accelerate frontend, but there are some big issues to overcome before that's a useful system or an approach that we take. And the problem is that there's an API mismatch between the ARBB VM and accelerate. So in the ARBB VM you have add reductions, multiply reductions. In accelerate you have fold, or something like that. And you have getter, scatter, reverse, rotate, and 10 or so other ways of permuting vectors in ARBB, and you have to permute that in accelerate. And then there's also the issue with the vector dimensionality, that you have 1, 2, and 3D vectors in ARBB and arbitrary dimensionality in accelerate. So before being able to use the ARBB as an accelerate backend, some kind of compilation needs to be developed that takes care of this gap in the functionality provided. So what I did now was, I was at home taking care of my daughter, and after a few months of that, my fingers were itching and I wanted to program again. So I didn't want to go doing work programming, so I stayed away from my GPU stuff, which I have been doing previously, and that's a dumb thing to say because I started programming graphics instead, but I've been programming GPU for general purpose computations, so now I was on leave and I did some graphics programming. And after a while I thought, well, let's parallelize some of this stuff. And I didn't want to do that using my GPU stuff, so instead I thought, let's look at the ARBB things again. And I did, but then I had the problem that I had the ARBB VM C bindings, very low level, or I had the unfinished accelerated backend. So I thought, let's just go for the direct approach. And just replaced C++ embedding by a very simple Haskell embedding. It just has very direct match between what EmbArBB provides and what ESL provides. So I had that one to low level. There I need some complicated compilation. So that's how this came to be. In this language, the same matrix vector multiplication looks like this. Very similar to the C++ version. You have the add reduction, the repeat row. The things that looks different is, I guess, the type. We have the expressions of d vector dimensionality 2 as an input. For people working in Haskell embedded languages, having an expression, the expression there doesn't, it's not anything strange, but what it means is these are abstract syntax trees representing these vectors that are the inputs and outputs. So the body of matrix vector multiplication also creates an abstract syntax tree, right? Few details. In this embedded language, you have two kinds of vectors, d vectors and n vectors that correspond to the dense and nested vectors of EmbArBB. A d vector can be one-dimensional, two-dimensional, three-dimensional, and an n vector could look something like this. It's an irregular container, and it cannot be further nested than this one level. So I think the nested name may be a bit misleading. There's a library of functions, of course. They have types that look like this, often. So the thing I just wanted to point out here is that the vectors have their dimensionality encoded in their type. There's difference between the dim 2 and 1. And in AddReduce you can see that the result vector is of dimensionality 1 less than the input vector. So it's also a little bit like in the REPA library where you have shape polymorphic functions. Then there's also, of course, you need something else to actually run this matrix vector computation. You need to do something more. And in this case, the EmbArBB model is a little bit like what you could be familiar with from the GPU model, that you have to copy your data into a kind of EmbArBB space before you can run EmbArBB functions on it. And also, there's some details here. For example, I say that F is capture network. I borrowed that word from the EmbArBB people. They talk about capturing functions. So what that does in this case is actually, network. You would produce an ASP. Capture would compile that and create an actual EmbArBB function. So this F is something that points out that compiled function in EmbArBB space.
What's its type?
What's its type?
What is the type of capture?
Yeah, that's a little bit complicated, and I must direct you to the paper. I don't have it in the slides. So following that, we copy the data into EmbArBB space, M and V. Those are also then identifiers pointing out that there is data in EmbArBB. I create something, a new vector for the result, and then execute F on M and V, put the result in R1. Very imperative interface, but I like C and I like Haskell, so I like this. and then we copy the result out and show it. Okay, in the paper we look at the number of benchmarks, and we chose to do image manipulation functions, programs. So we compute histograms and edge detections, and this one is supposed to be more blurry than this one. Doesn't look like it's from here almost, so image blur. And in all these cases we compared to the REPA library language. And of course, REPA is slightly different than this language. It's similar in some ways, but it's also more expressive with its high-order functions and faults and stuff. While we have the specific reductions. But if we compare favorably, maybe that can be overlooked to some extent. And in these cases we do. We have been, the edge detection case. Let's just focus on the non-dashed lines. Those compare the same thing. And we are performing slightly better, or quite better, than in all of our cases. On this slide I also put sequential C and EmbArBB, the C++ version, which of course those two lines, they fall on the same EmbArBB and this Haskell embedding, they fall on the same line, so it's on one line. And that's to be expected because we only compare the execution time of the actually captured function. And if there were differences there, that would be strange. But still better than the advanced function. And now a few words about the implementation. This is a very direct approach. I chose to, while I was doing this, I looked a lot at the Nicola language, and they used an untyped expression data type to represent the language. So I do the same. Then they use phantom types to be the type interface, and I do that also. The thing to look for here is, well, the op at the very bottom, which takes care of most of the EmbArBB functionality, depending on which opcode you put in there. Other than that, there's conditionals, and there's call and map, which could be interesting as well, because there I borrowed also from Nicola the approach. So R is the monad of the reifier that I use to turn these ASTs into tags, and the generator contains all the information needed to actually generate an EmbArBB function from a Haskell function. So it contains the tag, its type, and things like that. So that's how I take care of the map and call situation. Very similar to Nicola's VApply. So that's where that comes from. And the encoding of dimensionality in the types looks like this. This is nothing new either. This is what, stolen from the REPA people, more or less. Maybe much simplified situation. There's so many classes and stuff involved when looking at the code that I get lost. But I sort of distill some kind of core that seems to work in this setting. So I think of it as a cons of types and a type representing 0, and then the different dimensionalities are represented by different lists of types. This is the implementation of attributes, and I'm just showing it to show how it is represented by the op constructor in the expression AST. So it's op and then an opcode, and then it's operands in a list. So the expression data type was untyped, but phantom types supply a typed interface. It's a deeply embedded language. I use the stable names module for sharing detection, and I took a lot of influence from Nicola implementing column map and other things. So that was just a big hash. I've mentioned that REPA, data array accelerator related, but these are more expressive languages. They have higher order functions and folds and cool things, arbitrary dimensionality on arrays. They execute on GPUs, and REPA executes threaded, not vectorized, at least not earlier. And Nicola was the main, code-wise inspiration while I was working on this. They also have years. For the future, there's lots to do. That support for tuples as elements of vectors. This is something that the C++ system already does. So they perform AOS to SOA transformation, array of struct to struct of array. I want to see if it's possible to support higher dimensionality of vectors as well. That means some kind of compilation from whatever dimensionality vector you use in your program down to 1, 2, or 3-dimensional vectors. The overall robustness of the system needs to be improved. It's a work in progress, definitely. But we get good performance, the little implementation effort, by simply using the EmbArBB system. So the previous talker had like a chart with ease of use and performance, and magic happens here, or something like that. So we kind of say that let EmbArBB beat the magic, and we give us that ease of use. It's a simple programming model. We get threaded vectorized code portable on multiple CPUs, and even the many integrated cores, the EmbArBB system, they say in the article that describes EmbArBB, at least. We'll see when it comes out. I wonder if it also will support GPU execution in the future. That would be good, since Intel CPUs have GPUs right in there in the same chip, so that would be very good. One downside is that it is closely tied to EmbArBB, so the usefulness of this embedded language very much depends upon, what will Intel do with EmbArBB in the future. Thank you.
Questions? So in your example, you had to explicitly specify the length of the vectors. So what will happen if you specify the wrong length? Will you get a TSEC fault or a Haskell exception or what?
You will have problems. Yes, exactly how they materialize. You will probably get to tell what I think is something from the EmbArBB runtime about mismatches in sizes.
You showed the interface to your library is somewhat imperative. You have to allocate space for the result and then copy it in. And you said, well, I like C and I like functional programming, so this is what I do. But supposing I don't like C so much, can you give me a more functional interface to this that makes it look more as if I'm manipulating values that are arrays, immutable arrays?
Yeah, definitely. I think that someone who's into that kind of thing could craft it.
I said you.
But when I did this, I thought of it as in a slightly different way, because the main coding that you will do is functional. It's the small functions that you create, or large ones if you do, and then at some point there needs to be an interface. And
I see. So it's just right at the end.
Yes, it's right in the end that you do this. And up to that point, you will express using function composition and map and very functional.
I just have a question about vector fusion. Is that performed in the EmbArBB VM, or do you have any support for it?
It's everything that's optimizing or anything like that is done in the VM. And they do fusion, they say.
question about providing a functional interface. So it sounds like if you wanted to, you could provide a run like accelerates run, except it would be more implicit as far as when recompilation happens and when stuff is copied, just like accelerate. But it sounds like it would be, say, Haskell, unlike accelerate and maybe REPA, which are non-deterministic and cheating. Is that true? So, for example, those exceptions you mentioned earlier, the size exceptions, are those deterministic? Will you always get them on every run? If you give the wrong matrix sizes?
Well, every time you run it on something that's incorrect in size, I think you will.
Okay. So there are no exceptions that would occur non-deterministically here because of the interface between Haskell and EmbArBB?
I think not.
As for the performance comparison with REPA, can you just say whether REPA, I mean this is on the same machine, it's a multi-core machine, and does any one of those systems generate like vector instructions like SEC or AVX, and is there a difference?
So all of the comparisons are made on the same machine, definitely, and it's a 4-core machine with SIMD capabilities, 8 threads. And the REPA library does not use SIMD, at least not at the time I did this, I don't know at this precise moment. The EmbArBB uses SIMD, AVX, which is what I did.
Could the differences be attributable in the
I
cases
think
that
that
show to the use of
it looks like the SIMD instructions could be it that makes the difference.
You probably know that REPA 3 uses type tags to distinguish different array representations. You've not seen that, so but it occurred to me that it'd be quite cool if your representation of arrays was just another type tag in the REPA sort of suite. Then it might make the programming interface seem more, that you can move from one implementation of arrays to another just by changing a type, or by changing a code.
Yeah, that's definitely something to do. Yes. Thank you.
All right, I think we should stop him here now. Let's thank the speaker again.